Okay, so good evening, everyone. Today, uh, we are going to start session 7 that will be taken by Mohammad Ahsan Halimi. Mohammad Ahsan Halimi received his PhD degree in Electronics and Communication Engineering from National Institute of Technology, Silchar in 2023. He worked as a senior faculty at NCPUL Dream Center jointly run by National Institute of Electronics and Information Technology, NELIT, Chandigarh, and New Delhi. He worked in the project entitled Skill Development in Electronics Hardware during 5th February 2020, 2014 to 31st October 2014. He also worked as an assistant professor in the Department of Electronics and Communication Engineering, Ramakrishna Siddharth Engineering College, Vijayawada, from 2023 to 2024. He is currently employed as a postdoctoral fellow at the Research Center for Communication Systems and Sensing, King Fahd University of Petroleum and Minerals, Saudi Arabia. He has published 18 journal papers, 9 conference papers, and his research interests include RF energy harvesting, RF rectifiers, microwave antennas, reconfigurable antennas, wireless body area network features. So now I would request Dr. Halimi to start his presentation. Thank you.
Thank you, sir. Good evening to all. Um, Thank you, sir. Thank you very much for giving me the opportunity to present here for this faculty development program.
Thank you.
So today I will present about matching network and filter design challenges for radio frequency energy harvesting and wireless power transfer applications. Here I am a postdoctoral fellow interdisciplinary research center for communication system and sensing in Fahd University of Petroleum and Minerals. And these are the outlines I will cover. Backgrounds of energy harvesting, two emerging areas. That is RF energy harvesting and wireless power. Applications of RF energy harvesting. Key components of RF energy harvesting or WPT system, that is retina, and different components like receiving antenna, matching network, Schottky diode, DC pass filter, and different rectifier and matching network classifications, and some examples, and some design procedures for rectifier and matching networks. Before coming to the our main topics, let me to introduce my universities. I joined here King Fahd University, Petroleum and Minerals. It was founded in 1963, established in 1963, and with this university having QS World Ranking 101 in university categories, and engineering and technology categories, it has QS World Ranking 80, and if you look here for petroleum engineering, it has world ranking 2nd, and for electrical engineering, it has a world ranking 62. There are various research facilities available here. We have several equipment to do research. I have not included each and every, but I picked some of the components with the omnidirectional antennas. Using this omnidirectional antenna and a spectrum analyzer, we can check the available ambient power in the environment near to the to any nearby environment, and this is a spectrum analyzer, and as well as vector network analyzer and signal generator mode. We can change the modes. It works up to 50 gigahertz. Up to 50 gigahertz. And this is a signal generator. We can supply power for a rectifier circuit on any power amplifier. Now, let me come to my main topic, background of energy harvesting. Energy harvesting is the process by which energy is derived from external sources, captured and stored for low power devices, like those used in wearable electronics, wireless sensor networks, and any low power devices. And there are many techniques and many categories of energy harvesting. Thermal energy harvesting can use to convert thermal energy into electrical energy using Seebeck sensor. As we know about Seebeck and Peltier effect, that if there is a temperature difference, then we can convert that temperature difference into electrical domain using Seebeck sensor. We have mechanical energy harvesting, piezoelectric sensor, mechanical resonator. But our intention is about RF energy harvesting. So it is a case of electromagnetic energy. RF energy is electromagnetic energy at a high frequency. So to harvest electromagnetic energy, we should have our RF sensor that is rectina in our case. So RF energy harvesting is the process of converting RF energy into electrical DC. The device which is used for RF energy harvesting is rectina. Rectina can be used for converting RF energy into DC. So we have two emerging areas where rectina can be used. So first one is RF energy harvesting. RF energy harvesting, as I told, is the technique to convert, to capture RF energy from environment and convert into usable DC power. But the basic difference between RF energy and the DC, you will see here. The second emerging technique is wireless power transfer. It is the technique to transfer electromagnetic energy from one place to another place without using wire. So we have two techniques. Then what is the difference between RF energy harvesting and wireless power? Both having, in both cases, we are converting electromagnetic energy into DC. So this is the conceptual block diagram for RF energy harvesting and wireless power transfer system. So in RF energy harvesting, we should have our own, for RF energy harvesting uses ambient RF sources. So we have various electromagnetic energy from routers, for transmitter and mobile radios. So we can convert these electromagnetic energy into DC using RF energy harvesting techniques. So for wireless power transfer, we should have our own intentional RF source dedicated to provide RF energy for harvesting. This is the difference. For RF energy harvesting, we are focusing on ambient, and for wireless power transfer, we should have our own intentional RF source. So if you look in this diagram, conceptual block diagram, here you can see base station, that means transmitter section. This is receiver section. At transmitter end, we should have RF power generator generate RF energy, and that energy can be transmitted using a transmitting antenna, and that energy we can capture at receiver end. This is at receiver end. Receiver end, we can capture electromagnetic energy using receiving antennas, and rectifier can convert this DC. Here we have RF energy. Here we have RF energy. At this point, we have DC after passing through rectifier. Rectifier convert this RF energy into DC. and the load may be any low power devices or any resistor. So if we consider about this part, this is we can say that this is RF energy harvesting or retina. But if we consider whole parts means these parts, we can it will be termed as WPT system. WPT system. This is RF energy harvesting system. The complete is the WPT system. Why? As already told, I told about we should have dedicated power. If we consider the intentional transmitter and this receiver, then complete system can be termed as a WPT system. Otherwise, at receiver wing system section or retina, we can say this as a RF energy harvesting system. So RF energy harvesting is an energy conversion technique employed for converting energy from the electromagnetic fields into electrical domain. We have various sources like Wi-Fi routers, mobile transmitter, base stations, mobile phone, cell phone, and so on. So these various RF energy can be captured using a antenna and convert into DC in RF energy harvesting. Why RF energy harvesting? Is to have a free energy, eliminate cost to hardwire, powering battery-free devices. Battery-free devices, because sometimes it, for example, if we are working on implantable sensors, so if we have a battery in the implant with implantable sensor, so we need to replace time to time, and for each replacement we need to do surgery. So RF energy harvesting and WPT system can be used for implantable devices, and we can eliminate battery and placement flexibility because of no hard wiring. So placement flexibility we have, and transparent charging. So these are some example of RF energy harvesting and WPT system. Some applications. So in figure 4, this is a LCD watch, and this is mobile transmitter. This is LCD watch. This is retina. This is LCD watch. Here, LCD watch is operating by captured GSM signal. It means 1.8 gigahertz signal when mobile phone is ringing. Here, when mobile phone is ringing at then at that time this antenna will capture that signal, and based on this retina convert this. This antenna will capture the signal, and this will convert into this. This is RF. Now it is DC, and DC will be because of that signal. This LCD watch will turn on. Similarly, here is we have temperature and humidity sensor, and it will operate with the similar techniques. And some other techniques means for wireless power transfer for biomedical implants. Here we have intentional transmitter. Using this patch antenna, we can transmit if we have signal generator, power amplifier. Using that, then this antenna can transmit the signal, and implantable antennas can capture this energy, and implantable rectifier can convert this into DC, and using that signal, implantable sensor can operate properly without using any battery. So for each and every case we have retina. So now we will discuss about the key components of retina. we should have receiving antenna, and RF filter, matching networks, Schottky diodes, DC pass filter, and load. So the main objective of retina design is to obtain high conversion efficiency. The first approach is to receive uh, energy using receiving antenna and convert it into DC. So this is the uh, uh, component level discussion we will do here. So receiving and harvesting antennas can capture electromagnetic energy from environment. Based on the condition, which the antenna should have some specific performance requirements. So it must operate at available RF power. It should have high gain. Why high gain? Using Friis transmission equation, we have P received should be equal to P transmitted is proportional to P transmitted power, and already we have discussed here. Here, received power can be calculated using it has a gain of receiving antenna, gain of transmitting antenna, wavelength, and distance between transmitter and receiver. So, received power is directly proportional to transmitted power, gain of receiving antenna, gain of transmitting antenna, and wavelength of the signal, and distance between transmitter and receiver. So we should have high gain. If we will have high gain, so is proportional to G gain. So if we have high gain, then it will capture more energy, and we should have more output power. Sometimes multiband antenna can to capture signal from multiple sources, and RF filter is responsible for rejecting unwanted higher order harmonics generated by the nonlinear rectifying elements. We will discuss in the next slides about nonlinear rectifying elements. So that due to that nonlinearity of Schottky diodes, it generates harmonics. We need to reject that unwanted harmonics, returning back to antenna, and if that harmonics will go back to the antenna, then at the same time antenna will work as a transmitter, and the efficiency will be and capture power will be reduced. So the matching networks, after converting capturing the RF energy by antenna, it should be forwarded to rectifier. Okay, so this is antenna. If after capturing the energy, it should be transmitted to rectifier. So we need to design a matching circuit. So rectifier input impedance without matching network Zin should be calculated. And for example, this if it has 50 ohm impedance, so we need to introduce a matching networks that transform this input impedance into 50 ohms, so that maximum power should be transfer from antenna to rectifier circuit. Otherwise, we should have if we will not use matching circuits, the most of the power will reflect back to antenna, and there will be very few amount of power available for rectifier to convert it to DC. So we need to use matching circuit to efficient transfer of received RF power by antenna to rectifier circuits. So we have different types of matching circuit, lump component based LC matching circuit, microstrip single step matching network, dual step matching network. These are popular, and we have many more types of matching networks. But these three are very popular to design a matching circuits. So now Schottky diodes modeling. So we have third component is rectifier. Main component is Schottky diode. Schottky diode is responsible to convert electromagnetic energy into DC. So for modeling these Schottky diodes, from data sheet we should have all these values, and we know this is the Shockley equation, diode current equation, and it is very popular as a Shockley equation. And this is the Schottky diodes model in ADS, HSMS 2860. So these diodes and these parameter you can find in a SPICE model and data sheet. Data sheet of HSMS. A data sheet of this HSMS 2860 or 28 any diodes if you use in data sheet, this parameter will be available. Using that parameter, first we need to model Schottky diodes. These are the parasitic capacitance and parasitic inductance and parasitic capacitance from data sheets. At high frequency, we know that at the lead between two leads, anode and cathode, there will be some capacitance between this, and each leads having its own inductance. So this is the parasitic inductance and capacitance at high frequency. So rectification principle, as I told, this is the Shockley current equation, and if we apply Taylor series expansion, then we if we simplify this, then this diode current will convert will have DC power, fundamental frequency component, second order, third order, fourth order, and so on, higher order components, infinite number of components. But at the end of rectification, we need only DC power. We need not this these harmonics. So we need DC. So a good behavior to block signals other than DC, because we need DC at the output of the rectifier. So we need DC pass filter in DC pass filter. This DC pass filter will block harmonic signals. Harmonic signals means fundamental frequency components, higher order frequency components that DC pass filter will block, and it will pass only DC components. So the classification of rectifier circuits, we can use diode based rectifier, MOS based, CMOS using CMOS. Also we can design CMOS Schottky diodes. We can design rectifier circuits based on topology. We have series rectifier, shunt rectifier, voltage doubler rectifier. Based on operating frequency, it may be single band, multi-band, broadband, and based on operating power, we should have low power rectifier, high power rectifier, and wide dynamic rectifier. So single band, multi-band, and broadband rectifier, we have multiple ambient energy available in the environment. So we can convert that energy, RF energy, into DC using single band, multi-band, and broadband. Multi-band rectifier can be used to convert multiple electromagnetic energy signals simultaneously into DC. And if we design a broadband rectifier, broadband circuit, it can convert all the signals coming under this umbrella. So a broadband rectifier has similar task like a multi-band rectifier, multi-band. So we can design either single band or multi-band or broadband matching networks based on our requirements. So single band single band rectifier can convert mm, electromagnetic energy, uh, any one electromagnetic energy into DC. For that, particularly designed, we design matching networks. Matching networks especially are very crucial for designing a retina, because if we match uh, uh, antenna circuit and there is some sounds.
Yeah, I can see that. Just a minute.
Okay, can I resume? May I resume?
Yeah, yeah, yeah. You got
Okay.
it.
So based on the requirement, we can design a multi-band or broadband antennas. For a multi-band retina, we need multi-band matching networks, and for broadband, we need to design a broadband matching network. There are various techniques to design a multi-band and broadband matching techniques. Single band matching network is somewhat easy because we have already mm, know about a Smith chart, how to use a Smith chart to convert any arbitrary impedance to any 50 ohm or any other impedance using for single band matching networks design is somewhat easy because you know uh, how to use a Smith chart. But for multi-band and broadband matching network design is somewhat difficult. So we are generally using a Smith chart online tools. Sorry, ADS providing tools for to design a Smith chart utility and some other tools to design a matching networks, broadband and multi-band. And single band also. Single band is somewhat easy. So these are the techniques. We can design multi-band matching networks using two methods. One method is using single multi-band matching networks, and one method is stacking different matching networks. For example, this is a single band. This is also single band. This is also single bands. And after stacking this from simply, for example, this is ZL, and this is Z is equal to 50 ohm, for example, 50 ohm. So using a single matching networks, if load impedance converting 50 ohm at the rate F1, at the rate F2, at the rate F3, because I told the current following through Schottky diet follows Shockley equation. Shockley equation is a nonlinear equations, and so the input impedance of rectifier varies with input power, operating frequency, variation of load. So if there will be variation in load, the input impedance will this impedance will be changed, and if there will be at each and every frequency, the ZL will be different, and each and every power ZL will be different. So at the end of the time, we need to convert this ZL to 50 ohm at frequency F0, at frequency F1, at frequency Fn. You either using this single matching network techniques or these techniques. Here in the second techniques, this X minus Z JY converted to 50 ohm using at frequency F0 using this matching network, at frequency F1 using this matching network, like that. So we have two techniques using the first techniques. This is the one of the example of triple band matching networks for triple band rectifier is designing to convert three electromagnetic signals into DC. And this is the second techniques. Second techniques. We have a hybrid junction and for, three rectifier at one at 1.8 gigahertz, one at 2.1 gigahertz, and one at 2.45 gigahertz. And this is the input ports. This is the input ports, and these are all three ports are used to stacking this rectifier. So each ports connected with one rectifier, and finally we have a triple band rectifier. So we can use any one techniques to design a multi-band matching network or multi-band rectifier. So this is the some broadband rectifier techniques. In these techniques, this high pass L section are utilized for lower frequency bands, and for upper bands, for example, this is the FL, F upper. For this frequency upper bands, this inductive L section has been utilized by MM Mansoor, and finally they got some broadband performance here using a single matching networks. Here the two different rectifier has been stacked. One for this is lambda by 8 at lower frequency. This is lambda by 8 at upper frequency, and at lambda by 8 at lower frequency. This is lambda by 8 at upper frequency, and finally this rectifier able to operate from a lower frequency to from FL to FU for a broadband. And this is some other techniques using a single broadband matching networks at the central frequency. Central frequency means this is FC, this is FL, this is FU. This is lambda by 8 at the rate FC, lambda by 8 at the rate FC. One is open circuit, one is open circuit, one is this is short circuit. Open circuit and short circuit transmission lambda by 8 transmission line at central frequency has been utilized to design a broadband matching networks. Here some taper techniques, taper transmission line has been used. Taper 1, taper 2, taper 3, taper 4, taper 5, and using these techniques. There are many other techniques. Some of the techniques are here. So low power and high power rectifier. We have discussed about in the Schottky diode modelings. We have various Schottky diode spice parameter. For example, yeah, these parameters. We have breakdown voltage. This is breakdown voltage, and some threshold voltage. So threshold voltage, if we have a low threshold voltage, the rectifier will operate at lower at low available power. If we have high threshold voltage, because the rectifier needs some power to turn on. That is known as a threshold voltage of that Schottky diodes. So for designing a low power rectifier, we need to select such a Schottky diode having low threshold voltage. So VT. For low power rectifier, diodes should have low threshold voltage. For high power rectifier, diodes should have high breakdown voltage. Here you can look at can see the breakdown voltage impacts. If breakdown voltage is increasing, this is the breakdown voltage breakdown. If for 3 volt, this is for 7 volt and 12 volt breakdown voltage. If we have high breakdown voltage, rectifier can sustain high power and it can handle high power without burning. So designing a low power rectifier, we should have a low threshold. We should have low threshold voltage, and for designing high power rectifier, we should have high breakdown voltage. But the available Schottky diodes in the market, if we go for high threshold voltage, sorry, if we want to purchase high breakdown voltage, so it have a high threshold also. And if we go for low threshold voltage, then it have low breakdown also. So either it can work out as a low power operation or high power operation. So if you want to design such a rectifier that can operate for wide power range, wide dynamic power range, we should have some techniques. So here, to design a wide dynamic rectifier, as I told, the input impedance of rectifier is a function of input power, frequency, and load. If input power will vary, the input impedance rectifier ZL will vary according to the input power. So if the one of the techniques is this, we calculate the input impedance at low power, calculate input impedance at high power, and accordingly we can design a matching network. So this this is a high low threshold diode, and this is a high breakdown voltage diode. So this can operate at high power level. This branch can operate low input power. If we have a low available input powers, then this branch can work efficiently at high input power condition, high power condition. This branch can work efficiently. And for example, this and the input efficiency. So if for low threshold voltage, for example, this can operate here. For the high operate power, this can operate here. So overall, we can have this. We can have like this. Finally, it can operate for odd range. Here also, two diodes, low power diodes having low threshold voltage to operate at low power. This branch can operate at high power because we have two diodes, and VBR will be add, the threshold will also be add. So this can work at high power condition, this can work at low power condition, and accordingly we can design such a rectifier that operate for broad input power range. So this is the designing procedure for rectifier circuit. First, we need to have we need to define our goal. Goal maybe at what frequency we want to design a rectifier, or what frequency we are going to design a rectina, at what output power we need, and at what power level, available power level, we want to convert into that power into DC. So first we need to define the goal. Goal may be about about frequency, about power level, about power level, uh, what output we need, output power requirement. After this, we need to we need to go for selection and modeling of diode. Selection and modeling of diode. So, how to select a diode? As I discussed earlier, uh, diode should be selected based on available power. If we have we want to design a rectifier operate that can operate at low power condition, so we need to select such a diodes having low threshold voltage. And if we want to design such a rectifier that can operate at high power condition, so we need to select such a diodes having high threshold voltage. After that, we need to go for modeling of diodes. So how to model? As we discussed earlier, we have Schottky diode, some spice parameter, spice parameter in the data sheet. In the data sheet, using that spice parameter, we can model the Schottky diodes. After modeling the Schottky diodes, we need to go for topology, either series rectifier, either shunt rectifier, either voltage doubler rectifier, um, or voltage multiplier. Based on that, that is topology. Which topology we want to use? Series, shunt. Voltage doubler is the combination of series and shunt. So at a low power, mostly we are preferring series or shunt rectifier. At high power, we can go for multiplier, multiple stage rectifier or voltage multiplier. But if we use voltage multiplier, number of Schottky diode increase, it means more input power can be consumed by the Schottky diode itself. So the efficiency will degrade. So we need to find the trade-off between number of stage or available input power. But at the same time, for if we want the higher output voltage, we can go for voltage doubler or voltage multiplier. After designing, for example, this is a load, this is a DC pass filter, and suppose this is a D1, D2. We need to check the impedance. We need to check the impedance as a function of frequency and input power. We need to find the input impedance, because we have a antenna here. Hey, this is antenna, this is rectifier. We want to transfer this signal here. If we have ideal matching networks, complete power captured by the antenna can be transferred to the rectifier circuit, and that the complete power can be converted into DC. So in practical, we need to design first we need to check the input impedance. For example, if this is 50 ohm, this is Z input, X minus JY. So we need to use matching networks. Using this matching circuit, this X minus JY input impedance should be transformed to 50 ohms, so that the complete maximum power captured by antenna can be transferred to the rectifier for converting into DC. So, and low pass filter or DC pass filter can we are using this. This is the DC pass filter, low pass filter, DC pass filter. Sorry, this is the DC pass filter to smooth the output voltage. After finding this input impedance, we need to design a matching networks. After designing matching network, we need to check the performance of rectifier. Performance of rectifier means output voltage, V out, power conversion efficiency, sensitivity, breakdown, power handling capability, like that. And these all three can be using a single graph. We can check this sensitivity, breakdown, and power conversion efficiency. If goal achieved, we can go for fabrication. Otherwise, we need to optimize matching networks and we need to check the performance, and this iteration loop should be continue. For example, one of the example, we defined the goal 2.45 gigahertz Wi-Fi output for watch, Schottky diodes we have select, topology we have select, voltage doubler, input power at what a function of operating frequency, function of input power, sorry, input impedance at the function of frequency, resonant frequency. First, we have calculate the input power. This is at 2.45 because this is at 2.45 gigahertz. We check the input impedance. Imagine we should have 50 plus J0, but we don't have this. For example, here it may be 30 minus J100. So after designing a matching networks, here we can see that it has 50 ohm, 50, this is 0, 50 plus J0 impedance. After this is without matching network, this is with matching network. After designing matching networks, we can check, if we check the performance, the rectifier can operate at 2.45 gigahertz and at this input power 5 dBm input power efficiently. So this is the Smith chart utility. This is available in the ADS software. So this Smith chart we can utilize to design a proper matching network. And first, as I discussed, as I told that we need to the input impedance of rectifier vary with input power and frequency. So at for example, our goal is at any arbitrary frequency, 2 gigahertz, 3 gigahertz, 4 gigahertz, 5 gigahertz, anyone. So that frequency should be put here. We need to put here, for example, 2.45 gigahertz. Sorry, 2.45 gigahertz. Now, we need to design a matching networks at 2.45 gigahertz. So we need to check the load impedance. We need to put what is the load impedance without matching networks. That should be put here. If we click here, we need to put value here, and this is source. Source impedance, it may be 50, it may be x minus jy, and for example, this is x minus jy, x minus jy, this is 50. So then we need to select some components from here, either open circuit stub, short circuit stub, series transmission line, different inductor, capacitor. Preferably we are using these components to design matching networks. So we can first we need to check the input impedance. We need to fill here, and source impedance maybe 50, or after that we need to select some components from here. For example, I use some different transmission line, TL1, TL2. This is transmission line from this. This is short circuit transmission line from here. And after this, you can see that this input x minus jy, we are very close here. This is 50, exact 50, ideal matching, ideal conditions. But we should have approximately 50 plus, 50 plus j. Exact for broadband matching networks, it is very difficult to find exact 50 for each and every frequency. For single band, it is somewhat easy to be more close to 50 ohm, but for multiband and for broadband rectifier case, it is somewhat difficult. So, for example, this is VSWR2 circle is equal to 2, or S11 is equal to minus 10, approximately 2 circles. So if we can go close to this, it will operate for broadband and multiband case. And for single band case, we can easily go to these points. So after that we need to go for build ADS circuit. If we click on this build ADS circuits, these transmission line parameter what we have used, electrical length and operating frequency, everything will become, and we can use that matching networks into our rectifier. I think this tools is very helpful. And after utilizing this matching network, we can see here the maximum level is 0, means here it is 0 dB. Minimum is minus 25, means here it is minus 25. So it is somewhat here minus 10 dB. So we can see that it can match from here to here. It is 1.5 gigahertz here, and upper is 3 gigahertz here. So it may be approximately 1.8 to 2.9 gigahertz, maybe. So using this Smith chart utility, we can design matching network. Now some example from my existing works. This is dual band rectifier for 5G, 3.5 gigahertz 5G and 5.8 gigahertz Wi-Fi bands operated. So at this frequency, 3.5, 5.8 gigahertz substrate, we are using this Schottky diodes modeling and rectifier, series rectifier topology we have selected. And this is the design procedure. This is the This is FSMS 2860 and series. And series 05. And this is okay. To HSMS 2860 in series topology. And first we need to calculate load impedance, and input impedance may be 50 at 5.8 50 ohm at 5.8 gigahertz. So after single band wedging at f1 5.8 gigahertz we utilized, and that rectifier match at this operates. But now we want to convert, and using this Smith chart utility, this utility, using this we have designed this single band matching networks. And if you want, you wish, you can use Smith chart also. Smith chart technique is very popular, and in graduation also, and in textbook also you can find how to utilize Smith chart. So after that, we want to convert this single band into dual bands. So this exact single band is here, and I utilize half wavelength transmission line at the rate f1. F1 is 5.8. What will happen? Half wavelength transmission line. Half wavelength transmission line. Suppose this is a transmission line. This is ZL. This is ZL. ZS. Okay, sorry, here it is. So we have now we have input impedance ZL. What will happen if we use this half wavelength transmission line? What will be the tan beta L? This is the standard equation of transmission line. If beta is equal to 2 pi by lambda, tan beta L will be tan 2 pi by lambda. L is equal to lambda by 2. What we have used? Lambda by 2. Lambda by 2. So this pi cut, 2 cut is equal to tan pi. What is the value of tan pi? 0. Tan pi is 0. So tan pi, tan beta L is equal to tan pi is equal to 0. So what will happen? This will be equal to 0. This will equal to 0. So it will be equal to Z naught ZL upon Z naught. So we can cut this ZL to ZL. It will be ZL. So here Zin will be equal to ZL. Z will be equal to Z will be equal to ZL. If we use what it means, it means if we utilize half wavelength transmission line here, and if we there is no any involvement of width of the transmission line, it has only involvement of the length of the transmission line. If length is fixed to lambda by 2, either the width of the transmission line is any width, it will not impact. What will be the load? It will be the Zin. Zin will be equal to ZL even after any arbitrary characteristic impedance. There is no role of Z naught here. There is no role Z here. Z in is proportional to Z naught also, length also, beta also, load also. But if we use half wavelength transmission line, then this will be nullified, and this will also nullified, and we have Z in it is equal to ZL. So using these techniques, we can see here, if we change this if we utilize this half wavelength transmission line, and if we change the width of the transmission line, it will not impact at this frequency. Here we the width of the transmission line, here I am changing, and after changing this width of transmission line, we achieve a second matching at proper width, and but it is negligible impact on 5.8. I hope everyone understand the techniques of half wavelength transmission line here. So this is the one techniques. So after using this half wavelength transmission line, we have this S11 power conversion efficiency, fabricated and measured results. And so now for triple band rectifier, we have we want GSM LT 5.8 gigahertz. A designed rectifier operate these three bands, triple bands. First, a single band rectifier is designed, then converted into dual band using the previous techniques, using these half wavelength transmission line techniques, using this half wavelength. First, this is a single band rectifier, and using I utilize again same techniques, half wavelength transmission line here. Step 2, step 1, step 2, step 3. Okay, so step 1 having single band, black color. It has some 5.10. After utilizing this half wavelength transmission line, we can see that it can step 2 is red line. We can see that we have dual band, red color. And after utilizing now, already we have discussed about this half wavelength, impact of half wavelength. Now, if we use quarter wavelength transmission line, what will happen? Tan beta L will be equal to tan 2 pi by lambda by 4. L is lambda by 4. In third stage, I utilize quarter wavelength transmission line. Then this wavelength will come, but it will be tan pi by 2. Tan pi by 2 means tan 90 degree. Tan 90 degree will be infinite. Okay. So this transmission line doesn't impact anything. It will be, what will be the impedance, input impedance at here? Same input impedance will be appear here at 5.8 gigahertz. But what will happen here? Suppose any arbitrary position here, what is the impedance here? Infinite. There is open circuit. Short circuit means 0. Open circuit means infinite. After utilizing this quarter wavelength transmission line, if we solve this equation using this, what will be the input impedance? Zin will be infinite. At 5.8 gigahertz, this impedance, if we look from here down, then impedance at 5.8 gigahertz will be infinite. Zin will be infinite. So it will not, again, it will not impact at 5.8 gigahertz. And then after tuning the width of the transmission line, we have achieved third frequency band. Here we can see that S11 at S11 and power conversion efficiency at after utilizing half wavelength and quarter wavelength transmission line. So and this is the performance of the triple band rectifier. This is S11 power conversion efficiency versus frequency, V output versus frequency, and this is the simulated and measured result. Now, one example is frequency selectable rectifier. Here the design techniques is after calculating ZA, how to calculate Z1? Using this formula? This formula? You can use this formula for finding this transmission line input impedance here, Z1. This is ZL and this is TTL1. So you can we can use that standard transmission line formula. Then again T and then again transmission line induct. And how to use these? For example, if we have Z3 here, and this is TL3, then this will be parallel. So we can, if for example, if we have ZX, so ZX parallel Z3. So parallel combination we can use this, and for detailed version you can check this this paper. Here I have detailed. You can find the detailed version of calculation, how to calculate series and shunt transmission line and capacitive effect, how to go back backward directions to calculate ZL, Z1, Z2, Z3, and Zin. You can find we can find here. And here, by changing the value of inductor, each and every value of inductor, we should have this Zin will match at different frequency. By changing the inductor values, the input impedance will be changed accordingly, because inductor having what is J omega L. Inductor, it is also a function of frequency. So here you can see the S11 impact of S11 with different value of inductor, impact on power conversion efficiency with different value of inductor simultaneously. We can see here, and this is the performance of the rectifier. Now, broadband rectifier, how to design a broadband in Smith chart utility. We already discussed about the broadband rectifier. So just I want to show you the impacts of Smith chart. Okay, at 3.3 gigahertz we have this is, for example, the center point. Ideal condition we should have for broad frequency range, we should have input impedance here 50 ohm, but I told the acceptable range is minus 10 dB S11, or VSWR is equal to 2. VSWR should be less than 2, or S11 should be less than minus 10 dB. So these are acceptable. So from 3 to 5.5 we can check here. This is VSWR is equal to 2 circle. Sorry, this is VSWR is equal to 2 circle. So it is approximately matched to 50 ohm, not exact. So for multiband and broadband, we should have close to 50 ohm, not exactly 50 ohm. If we find exact 50 ohm at one frequency, it will disturb the second frequency. So we should compensate. We should find the trade-off between these matching. So average should be less than 2 VSWR. So here we can see that it matched for paired frequency range, and this is the switch chart. So come to the concluding remarks. RF energy harvesting is the process of converting electromagnetic energy into electrical power, because most of the solid state device need DC power to operate. But antenna can capture electromagnetic energy from environment, but it unable to convert this electromagnetic energy into DC. So we need to have a rectifier circuit to convert that electromagnetic RF energy into DC. But before that, we need to design a matching circuit that is very crucial in for designing a RF energy harvesting and wireless power transfer system. Matching network is crucial, because if matching networks will be designed properly, means captured power by the antenna can be efficiently transferred to rectifier circuits, and now rectifier can convert this electromagnetic energy into DC using Schottky diodes. So for low, based on the power condition, we should select proper Schottky diodes, and based on the requirements, multi-band, broadband, or wide dynamic range, we should design a proper matching network. So selection of matching of a proper diode and designing a proper matching network is very crucial to design a wireless power transfer system or RF energy harvesting system or Rectina. So thank you very much to participate here and listen. Yes.
So thank you, Dr. Halimi, for your nice and informative presentation. So now I will ask all the participants that they can raise any type of questions related to RF energy harvesting or anything.
Hello, sir.
Hello,
I
sir.
have one question.
Yes.
Hello.
Yes.
Yeah, please go ahead.
Sir, am I audible?
Yes,
Yeah,
sir.
you're audible.
Okay. Sir, it was a very nice presentation. Can you please go to the last slide, that is slide number 37? That is broadband.
Yes.
Sir, here actually I am working on broadband rectifier. So how how I will choose the input power, as you have here written that with respect to frequency and S11 various input power you have chosen to check the S11, but here in Vout and PC you have written 0 and minus 5, I think 5 minus 5 dBm. So how we will choose the input power?
Actually, I told earlier, the input impedance of the Schottky diodes varies according to the power level also, or frequency. So for broadband, you have already selected the frequency. Okay. For example, 2 to 3 gigahertz you are going to design, then your second frequency is 2.5 gigahertz and so on. So frequency you have selected. So from that frequency, from that frequency range, this. But now come to the power.
Yeah.
Here you can see that at each and every power, the bandwidth is not same.
Yeah.
So because if you select a Schottky diode,
Sir,
diodes having a
your voice is not audible.
Okay, now I'm audible.
Yeah.
So you have already selected the frequency of operation. For 5G, it is 3 to 5 or 3.5 gigahertz, or 2.0 for Wi-Fi, it is maybe 2.4. So that is you have selected. Now you want about power, how at what power level, how to do. So here you can see at each and every power level, the bandwidth is not same. And
Yeah, yeah.
that based on the Schottky diode breakdown voltage, VBR,
Hmm.
breakdown voltage, and VT, threshold voltage. Threshold voltage is not given directly to in data sheet, but yeah, in some paper you can find that threshold voltage a particular current value, means forward voltage. So for example, you are going you are going to use HSMS2, breakdown voltage is 7 volts. So
Hmm.
accordingly you should select at what particular power level diode will operate without breakdown. It should be below that breakdown. For example, some power, some example case here any day. Okay, if
Hmm.
you convert this is the breakdown, impact of breakdown here. So it should be below that, power level should be below that. Okay,
Okay.
and this depends on the Schottky diodes, not about
Acha.
matching.
Okay,
This
okay.
depends on the Schottky diode breakdown voltage, V breakdown. So it should be less than that that breakdown voltage. And for some case, you may find here, it breakdown is something different. Okay,
Okay.
maybe it is 7 volt, 7 dBm. So based on the Schottky diodes breakdown voltage, it may be varying. So which Schottky diode you have selected, and
Sir,
you can.
actually, one more question. What is the difference between HSMS 2862 and HSMS 282? I mean 2C.
Okay, actually the earlier, for example, 28, I'm not exact, but let me say 2860,
Zero. Huh.
2862, 28662, for example, and sometime it you will find 286C and C.
B.
Both are same, are
Hmm.
B or C. But
Okay.
in earlier during fabrication, it just the changing of name. You need to check
Okay.
only the connection of diodes. Okay,
Okay. Okay.
connection of diodes. It is voltage doubler. Either it is B or 2. Don't worry about that.
Okay. Okay.
Okay, if you want to
Okay.
design voltage doubler, either 2862 or 286C. If both are having same, then go to anyone. There is no problem. Earlier, it was available in market using with some old name, but just name has been changed. Nothing else.
Okay, sir. Sir, actually, I have one more queries. That
Hmm.
is about you have one that is last graph simulated and measured V out with respect to
Hmm.
frequency. So,
Hmm.
how
Yes.
will you they show this graph in ATS?
Okay. Well,
Actually, I have checked many.
for for this graph, it is very simple.
Yeah,
Okay.
yeah, yeah,
For
yeah.
because we have three variables. One variable is input power. Second
Yes,
variable is resonate frequency. Third
yes,
variable is load.
yes.
So if you will use harmonic balance,
Hmm.
okay,
Hmm.
and then sweep should be P in
Okay.
for this case. For versus frequency, sweep should be FR. Sweep,
Okay.
but
Okay. So
sweep variable should be F
in harmonic
harmonic
balance,
balance.
sweep should be
Yes,
FR. No.
sweep variable should be FR. And
Okay.
at that case, you need to fix this input power and load. So
Acha.
you need to some parameters. One more parameters I need to remind. So one thing is harmonic balance, and one
Hmm.
is yeah, actually
LSSP.
not LSSP. Uh, some any more?
Hello, hello.
Yeah,
Excuse me, sir. Am I audible?
Yes.
yeah.
Yes.
Okay, sir. Thank you so much for your nice presentation, sir. I have a query, that is whatever slide right now visible, sir. There we have used you have used the copper conductor. That means that due to the dielectric nature. So, sir, if I do the tin plating over the copper, then probably the loss can be or loss value can be reduced, sir, because copper is generally very much affected by the environmental situations or environmental noises. So in generally in fabrication tin plating is done, sir. I know you, I think you know, sir, this. What about what about you are thinking about the dealing with the conductor loss for this?
Actually, if you will go for using gold or silver, for example, as we saw, gold and silver is more conductive, so then the loss will be, of course, low. So that is the case only. Sigma should be infinite. Sigma should not be infinity in real case. It will vary for. But if you will design anything using copper or gold or silver, everywhere we are considering sigma infinity. Okay, but actually it is not infinity. It is very high. So that high depends on this. So based on this, you can see. Of course, it has some impact. For gold, sigma will be more compared to copper. Sigma will be more high.
And then the cost will be automatically
Yes,
increased.
yeah.
Yeah.
Cost will be, so that's why that is also we need to find the trade-off which is available. So we are going uh, toward that way. And for the previous questions, harmonic balance. First things is, the last audience was asked some question about power conversion efficiency versus frequency, how to do this graph. So we need to
Yes, sir.
a harmonic balance, sweep variable should be frequency. You can
Okay.
also check this as a sweep frequency, and one more parametric, parametric sweep. You need to check parametric.
Okay.
Some you search in ADS parametric.
Okay.
In that parametric, you need to fix P in,
Okay.
and if it is HB1, okay,
Okay.
then
Okay.
HB1 should be fit here, HB1.
Okay.
Okay, then
Okay.
again use one more parametric sweep. Parametric sweep. Suppose this is parametric sweep 1, this is parametric sweep 2, parametric 2, or something different. Because ADS is not here, so I can. So in 2, so this harmonic balance is connected to this parametric HB1. Now this parametric should be connected to this. Here you need to use parametric sweep 1. This will be 2. This will connect it to parametric sweep 1. These parametric sweeps will connected to HB1 like this, and you can find this power conversion efficiency versus frequency. But
Okay,
you
sir.
need to fix out of 3 variable, load and P input. You need to fix, and
Okay.
you need
Okay.
to connect this HB and parametric sweep P1, para 1, para 2. You need to connect between these, then these, and then you can find. Any more
Okay, sir.
question?
No, sir. Thank you, sir.
Any other audience?
Any other participant?
Yes,
Do
sir.
you have any question?
Yes, sir. I have
Yeah.
one question. Hello, sir.
Yeah.
Should we use a single diode rectifier or a voltage doubler rectifier? Because if you use voltage doubler, the voltage will be increased, but conversion efficiency will be reduced. Okay,
Will be
and if you
somewhat
use
reduced,
single
yes.
diode, yeah, if you use single diode, then conversion efficiency will be increased, but voltage will be reduced. So which one should we use?
But you need to find the trade-off between that. One thing is trade-off. What your goal? What is your goal? That I told that this.
So which
Based
parameter
on
should we put more emphasis, PC or voltage, output voltage?
mm, power conversion efficiency. Because
PC.
if you want to publish in a paper, okay, your load will be fixed. Okay.
Okay, sir.
But if we go for any sensor, for example, these slides, 1 minute.
Hmm.
What is the load? Load is this. Okay.
Yes, sir.
And some results. Suppose if there is some that types of graph is not available in my PPT. Otherwise, we can find the power conversion efficiency versus load. Okay. But
Yes, sir.
and at what load we have more power conversion, we can writing in a paper. Okay.
Okay, sir. Okay, sir.
But for if you want to for real life application, you can find the impedance. Load is fixed. If it is this, we need to go for this, not this. Okay.
Okay, okay, sir.
So
Okay, sir,
what is the impedance of this sensor of this sensor? This is fixed.
Yes, sir.
For that fixed load values, we first operating frequency will be fixed, then load will be fixed in this case. But for just for rectifier or rectina applications, we can vary the load. For example, this is R1, this is R2. We have power constraint. In paper, we are just discussing about this value. Okay. But for real-time application, we cannot discuss about this. What is the impedance of this? Okay. We will discuss
Yes,
about this. So this is the difference between.
Okay, sir.
Anyone?
Sir, do you always need a band pass filter between antenna and the rectifier?
No, generally matching network is enough, sufficient for that.
That matching network will act as a filter or what? Sir?
Yes.
No, sir. In the previous slide, you have shown that after antenna, we need band pass filter, then matching network,
Yes,
then the rectifier.
If you use
Yes, sir.
yes, sir, I know that things. But the input impedance should be same. So in general, we are using only matching networks. And if you want particular, this will complicate the circuits also, but even matching networks is sufficient. But here DC pass filter, in DC pass filter, if you are using only capacitor, someone using some harmonic termination networks, also using some fan shaped stop or some different stop, then this will also
Radial stop.
Radial stub, yes. So matching networks and DC pass filter is more crucial. And out of that,
sir.
matching network has main role. And some harmonic termination. Yes. And even in matching networks also, if you are using some stub, that is calculated based on the transmission line, operating frequency, that is also working as a RF filter only. Some stub, particular frequency.
Yes, sir.
Otherwise,
sir, thank you, sir.
Otherwise, for example, S11 value. For example, if you forward this up to 10 gigahertz, for example, there will be some harmonic frequency. Okay, using that matching networks. If this harmonic frequency is not appeared using that matching network, it means that matching networks also working as a harmonic termination. Also, some harmonic terminations or some concept is also applied. Then only this is not available. Otherwise, some harmonic frequency components in S11 graph will appear undesired.
Okay. Sir, another thing I wanted to ask.
Yes.
The diode you have mentioned here, HSMS 286 series. Okay. So those diodes, as far as I know, their manufacturing has been stopped. It's not available in the market anymore.
In India, you may find SMS 7630. But in US, you can purchase. US, it is available. DG key.
Okay, okay. So no, actually, I have searched there also. It's not available. So
I purchased last
ac-
3 4 year ago. DGK
yes, sir.
also available and DG chip also available.
Yes, at
DG
that time
chip.
it was available. Right now it's not available. I have actually searched also. So instead
So
of
then
using that
forget
diode,
about 286C, 286C or B. Just name has been changed. In place of
okay,
2862, some B or C has changed. That's the first if, questions query was asked about that same thing. So maybe it appeared as a BC 286B 286C in place of
sir,
2862 2861.
can,
So,
can you use any other diode having the same spice parameter, that is electrical
yes,
parameter, as this? That
but according to that price parameter, you need to model the Schottky diodes. That's it.
yes, sir. That's what I'm saying. Because I found a diode in India. It's available. That
Uh, element
BAT03W diode.
14.
Yes, sir. Element
In
14. In element 14.
element 14, yes. Element
Yes, sir. In
14,
element
you can
14.
find some Schottky diodes. So according to
Mm.
that, you need to model this
Model this
diodes,
diode.
and you can use this.
Yes, sir. Okay, sir. Thank you very much.
Mr. Rajesh Das, you are from which college?
So I'm from NIT Silchar only, sir.
Okay, you are from NIT Silchar, and your who is the supervisor?
Sir, my supervisor is Gaurav Singh Baghel, sir.
Okay, so I think that you know Mr. Halimi. He is also from
Yes, sir.
NIT Silchar.
Yes, sir. He was my senior, sir.
Right. Yeah, okay. Okay. Thank you very much for your questions. So,
Thank you.
is there any other questions from any participants? I think that two-person already raised their hands. M Sweetline,
Hello,
Sonia Means. Yeah.
sir, I have a question. Sir, how to increase the power conversion efficiency of the rectifier? I mean, what factors I should keep in mind while designing my rectifier per 2.45 gigahertz?
Hmm.
Can you hear me, sir?
Yes, yes. For example, if you design this, we have these Schottky diodes we have used. One thing is for power conversion, sorry, efficiency
Sir.
versus input power or frequency. Okay.
Hmm.
One thing is some power diode needs to turn on. Okay. That
Okay.
power will be consumed by the diodes. Now it will start conducting. If power will go beyond that. Okay.
Hmm.
And it may go up to breakdown level, and then this will be VT threshold voltage
Hmm.
according to the proportional to, not exact, because in terms of voltage, this x-axis I am considering input power. Okay.
Okay.
This will be VBR, V breakdown voltage square upon RL. Okay.
Okay, sir.
So any diode can work between these power level. Threshold power level, it is proportional to threshold voltage, and breakdown power level, it will be equal to VBR square upon 4. Like this state forward, we don't have any equation, state forward equation to convert this threshold voltage to threshold power. Okay.
Okay.
In simulation we can see approximately, but breakdown power we have state forward equations, VBR square upon 4RL. So so this is fixed. For example, if HSMS2, it is 7 volt. Okay. 7 volt, and RL is, for example, 1 kilo ohm. Okay. The 7 square 49 upon 1 kilo ohm. 1 kilo ohm means 49 milliwatt.
Okay.
Okay. 7 VBR square upon RL. So if we do this, this may be 49 milliwatt. Convert to that dBm, it may be something, for example, 7-8 dBm jo bhi ho. Anyhow, so this will be 49 milliwatt. So these diodes cannot bear more than this power. Okay. With
Okay.
that, if you want to go beyond, then increase this VR square RL, or decrease this RL by means load value. Load value means this capacity, these loads, or any
Yes.
circuit loads.
Okay.
If you change this, then you can somehow change this power
Power
level
conversion efficiency.
on not efficiency. Efficiency is directly related to matching networks efficiency. If you will proper design matching networks, then it is fine. If
It will increase my power conversion efficiency.
yes, here I shown some graph. Yes, here. So using the matching networks, it is approximately 50 ohm, not exact. Here also in broadband rectifier, yes. In this case also, it is not equal to, after utilizing these matching networks, it is not equal to 50 ohm. But if you will go closer to this 50 ohm, the efficiency will be more.
Okay.
Or one more things is, if you you already calculated the input impedance, for example, here. This is check the input impedance as a function of power. For example, this is x minus jy. Okay? X minus jy. So we need not to design a matching network. Just design antenna, and in place of 50 ohm, use x plus jy port. Okay?
Okay.
In this case, you need to fabricate alone integrated rectifier antenna. So at that time, first it will be x minus jy, and antenna you need to design in place of 50 x plus jy, and then you can connect.
Okay.
Without using matching network.
Thank you, sir.
So any other participants? Do you have any questions? Okay, so I think that there is no more questions from the participants. So thank you, Dr. Halimi, for your excellent and valuable presentation. And the last thing is that many participants are asking for the PPT, sir. Sir, so if possible, sir, you can send me this PPT so that I can share the same with the participants.
Okay, sir. I will.
Okay. So, sir, thank you
Okay,
very
sir.
much. And good night.
Okay. Good night.